All right, for statistics part 4, we're going to look at a particular type of distribution called a normal distribution. And what this is that sometimes when we have a sample size that is sufficiently large, they're are distributed symmetrically. Remember, symmetrically means the same on both sides. With data, most data values around the center, a few outliers on either side, results in this bell-shaped curve, which you could see down below. First off, just give an example of data that could be collected where the majority of data would be in the middle and the data values that are less likely would be at the extremes. So you should have your own idea here. I'm thinking maybe like the heights of adults or something might be, because, you know, there's like average heights, but then there's some people that are really tall and really short, so that might spread out like that. But you put your own idea, what you think, where, again, majority of the data values would be in the middle, and those that are less likely, there's a few that are less likely, and those would be our extreme outliers. So again, this following curve shows a standard normal distribution. The symbol mu right here is the mean of our data set. The symbol here, this is sigma. This is a standard deviation. So we've talked about standard deviation. Remember, that was how much it deviates from the mean. Kind of talking about that. Oops. So it says describe the significance of each vertical region in the graph by looking at the value on the x-axis. So when you see 1 with the sigma, that's 1 standard deviation, 2 standard deviation, 3 standard deviation, and that's to the right. On the other hand, we have -1 standard deviation, -2, and -3. And really what that's saying is what happens with the normal distribution is there's certain percentages of data that fall within certain standard deviations. So we have that 68.2% falls within 1 standard deviation. So that would be looking at +1 sigma, -1 sigma. So in between there, it says that 68.2% of our data is there. Then we have that 95.4 will fall within 2 standard deviations. So within all of that, again, I'm not drawing it all the way down, but I'm kind of imagining all the data that's inside there. That's 95.4% falls within 2. And then lastly, we have that within 3, that's almost all the data. Within 3, we have 99.7%. So that means 0.3% of the data will lie on the extreme parts here. And so this is known as the empirical rule. So if we want to fill that in for the actual kind of spaces that are in our graph, we're going to have that 68.2 kind of split in half would be 34.1 and 34.1%. Then if we take the 95.4 and kind of split that, well, we already used up 68. So 95.4 minus that 68.2 leaves 27.2. And if we take half of that 27.2, that puts about 13.6 here and here. So altogether, if you add the current percents, it should add to that 95.4. And so then lastly, that within 3 standard deviations, 99.7, I'm going to subtract off the 95.4, and that gets me 4.3. So we're looking about 2.1% on each of these sides if I took half of that 4.3. And so when you add all those percents up, again, we should be at about 99.7. And some books have the tenths place off just a tiny bit from this, but we're going to use these for our work. So if I added 2.1 plus 13.6 plus 34.1, and then double that because it's the same on the left and the right, we're going to get about 99.6. So I guess we could go to 2.15, but we'll just say 99.6. It's really close. So that leaves on these left sides about 0.3 or 0.4. That's okay. All right, so for example number 1, on a particular college exam, the test scores follow a normal distribution. The mean score was 70 and the standard deviation is 8. What values correspond to 2 and 3 standard deviations? So I'm going to kind of sketch, and you should be doing this maybe on a separate sheet of paper. I'm going to kind of sketch a bell curve. I'm going to put right in the middle. Remember, the middle goes the mean. It told us here that the mean was 70. And then I'm going to go to the right, 1 standard deviation, 2 standard deviation, 3 standard deviation. So standard deviation is 8. So if I add 8, that would be 78. Add 8 again, that would be at 86. Add 8 again, that would be at 94. And going the other way, subtract 8. That would put me at 62. Subtract 8, that would put me at 54. Subtract 8, that would put me at 46. And so I just did within 3 standard deviations. So it says, what test scores can you expect to be within the following ranges? So it says 68.2%. So that's really looking at that within 1 standard deviation. That was that 68.2. And so what test scores do we expect there? Well, that goes from 62 to 78. Then the 95.4. So the 95.4, again, I'm following just up above, that's within 2 standard deviations. That's what we had said. That was our empirical rule. And so that would be between 54 to 86%. And then lastly, we have the 99.7. So that's really just within 3 standard deviations. That's 99.7. These are all percents. That would be from 46 to 94. Those are the test scores we would expect in there. All right, flipping over to the next page. They have it nicely drawn for us. And so I could stick in my percents just to help me out really quick. So 34.1%, 34.1%. This was about 13.6%. And about 2.1%, 2.1%. Okay, so based on the indicated percentages, again, I'm going to stick in what it had said. We're talking about that test. So 70 was our average. Standard deviation was 8, so 78. Oops. If we add 8 to that, that's 86, and then 94. And going the other way, we had 62. This was subtracting that 8. Okay, so here we are. Based on the indicated percents that we found in the original graph, what percentage of test scores are in the following ranges? So we're going to look at between 54 and 78. And so all we're going to do is add those percents that you see, which would be 13.6 plus 34.1 and 34.1, so that's the 68.2, which gets me 81.8% of that data will fall within that range. Next, we have between 70 and 100. So between 70 and 100. Well, 100. So all of this stuff would be half the graph. So we're going to say 50% of the data falls in there. And then lastly, we have between 78 and 94. So you can see we're going to add 13.6 and 2.1. Which gets me 15.7% about. All right. So now we want to talk about something called the z-score, and it measures how many standard deviations a score is away from the mean. So the z-score of an x, a value x, that's their piece of data, whose mean is that mu number and standard deviation is sigma, is given by this formula. For instance, in this problem, we have our mu equals 70 and theta equaling 8. If x equals 62, then our z would be -1. And you can see that up in our picture. So we see already that 62 is to the left of our mean, right? And it's off by 8. And so that makes it -1 would be the z-score, because that would be how many standard deviations it is away from the mean. It's -1 away. If we want to see that calculation, you can see 62 is the data point we're talking about, minus 70. Well, that gets you a -8. -8 divided by 8 gets you that -1. So if we're looking at like x equals 90, if I look at my picture, and I know it's getting kind of messy here, but if you think about it, 90 is going to be 4 away from 86, and it's 4 away here. So it's actually going to sit right in the middle. So just looking at it, I know it's between 2 and 3 standard deviations, and actually right in the middle, so I bet it will be 2.5. So let's look at that calculation again. And so what we're saying is that z-score, how many standard deviations away, we'll take 90 minus the mean divided by the standard deviations. You get 20 divided by 8, which is 10/4, which is 2.5. That's the z-score that we expected. So you can kind of use the graph. Sometimes they're a little bit harder, or they're more of a decimal that you can't exactly like see in the picture. So that's why it's nice to calculate the z-score by using that difference from the mean divided by that deviation. So if we're looking at 82, and I'm going to try something similar, 82 is 4 away from 78 and 4 away from 86. So again, sitting right in the middle, should be 1.5. So to see that calculation, again, we're going to take our data point, subtract our mean, divide by the standard deviation. 82 minus 70 is going to be 12. 12 divided by 8, I mean, you could reduce, that's 6/4, 3/2, 1.5, that's what we had said, 1.5. All right, so that, again, what we're saying with this z-score is that our data value 82 is 1.5 standard deviations away from the mean. Now for x equals 50, again, let's look up here. 50 is going to be 4 away. They keep being right in the middle here, that's convenient. 4 away on both sides there, so it looks like it would be -2.5. So again, we're calculating that z-score by taking the 50, subtracting it from the mean, and then dividing by 8 to see how many standard deviations away. So -20/8. That was similar to that first one though, so we know it will be -2.5. Now going the other way, if we want to find the actual test score related to the z-score, let's see, if we're looking at z equals -1.5, and I could use my picture, we'll back it up both ways. -1.5 would have to sit right in the middle between -1 and -2. Since that distance is 8, if I take 4 away from 62, or go the other way, add 4 to 54, that puts 58 right in the middle. So my guess, just by looking at the picture, is that my test score would be 58. Okay, so I drew a line on the graph for that location, but to use the formula, we know that z equals the data point minus mu over sigma. So -1.5 is equal to, we don't know the data point, that was my good guess, minus the mean divided by 8. If we multiply by that 8 on both sides, we're going to get -12 equals x minus 70, add the 70, and you get that 58 is equal to x, which is what we expected. So 2.25, so that's like 2 1/4, 2 1/4. Again, going to my picture, I want to see 2, so I'm on the positive side over here, and 1/4, so right in the middle between 2 and 2.5. So we already know that if we wanted to go 4 away, that would be 90 in the middle, so we really want halfway between 86 and 90, so that would be at 88. So it looks like 88 would be at 2.5. So let's check again with our formula. 2.25 is equal to x minus 70/8. So 2.25 times 8 on both sides, we're going to get 18 equals x minus 70. Add the 70 to both sides, and we get the 88 that we had seen just by thinking about and dividing that, because we know that our whole standard deviation is 8, so halfway would be 4, and half of that is 2, so that's kind of how it was counting to see 88 was 2 away from 86. And the last one here, we have 3.75. So let's kind of do it kind of backwards. Let's not locate it. First, let's write down our formula. And so we multiply both sides here by 8. We get 30 equals x minus 70. Add 70, we get 100 equals x. So at 3.75, we should be at 100. So let's think about what that would be. So if I went from 3 to, if I marked off 4, that would be up to 102. And so we know that halfway would be 4 away from 94, 4 away from 102, that would be 98. So that would be at 3.5 standard deviations. Now we said 3.75, so that's right there in between. And if you look at 98 and 102, the difference between those was 4. So if we go halfway, that would be increasing 98 by 2. That's 100. And then 100 is 2 away from 102. So it matches up on there as well.